Fuel cell. Fuel cell represents a class of battery describing one of the nowadays more smart solution in order to produce electricity in a green process. Why? Because fuel cells are particular types of batteries converting chemical energy in electricity with the generations of water or carbon dioxide as only byproduct. And so for this reason, we are looking for a real interesting types of batteries. And the future perspectives for these types of devices are extremely important and promising. So in general, it's interesting to say that a fuel cell is basically a galvanic cell, a battery, that with respect, for instance, a conventional battery in which at the very beginning we have reagent and the reactions start due to the consumptions of this reagent and proceed until the point in which the reagents are simply gone. Basically, for what concerns the fuel cell, we can theoretically promote the workings of the batteries since we are able to induce further fuel. What does it mean? So a fuel cell basically it works due to the reaction between a fuel, it could be or hydrogen or methanol sometimes, for instance indirect methanol fuel cell. We will see that types of cell in the second lesson dedicated to fuel cell. Or even hydrogen, I was said, in a reaction with oxygen. If you imagine, for instance, a situation in which the hydrogen is used as a fuel, in that case we are speaking about proton exchange membrane fuel cell, we will see why these terms. And in general, the reactions allowing the generations of electricity is basically the opposite with respect to the water electrolysis, one of the topics treated in one of the last lessons. So basically, in this case, since we are introducing a fuel, it could be gaseous, hydrogen or a solutions of methanol in water, since we are able to provide more and more fuel and obviously more and more oxidant oxygen, but this is not a problem since often in a fuel cell the oxygen is taken from the atmosphere as in metal air batteries. So basically we have a huge abundance and we do not to think about how much oxygen we have in the cell, since oxygen is simply taken from the outside, from the atmosphere. But so, since oxygen is not limited from a bulk, is present from the atmosphere and is one of the two reagents, and the second reagent is fuel, if we are able to provide a flux of fuel, a stream of hydrogen continuously, the batteries can work in a continuous way. So the theoretical life of these batteries, avoiding obviously any types of problems and corrosions and degradations of the membrane, for instance, is infinite if we are able to promote the introductions of fuel time after times and so on. So basically this is for what concerns the workings, the reasons for which fuels are so interesting. Even if we know that the output voltage is not so huge, we are speaking about an open circuit conditions that define an output voltage around 0.6 and 0.7 volt, not a real strong power. And for the reason often fuel cells are combined in parallel or in series in a finite torque in order to increase the maximum output voltage. So now what is interesting about the fuel cell is that this fuel cell, how we can maybe just before speaking about the structure summarize the main aspects, are a green technology. Why? Because we are producing only water or carbon dioxide as product. Obviously, always we are consuming a certain amount of energy in order to increase the entropy, because it's true that this is a green process. But obviously the fuel is extracted maybe sometimes from a non-green process often, and so obviously it's not completely a total green process, but it's significantly better with, for instance, other types of device. So it's a green process, we can have a long life, since basically we can increase the life just by introducing an additional amount of fuel. So continuous fuel streams inside the batteries can ensure continuous life of the batteries. But we can have even some problem concerning, for instance, the fact that we have low output voltage and since we need, for instance, a steam of fuel as hydrogen or methanol for some application, these types of systems it cannot be used. So now it's interesting to introduce what is the structure of fuel cell. So the structure of fuel cell, as always, is composed with an anode, a cathode and an electrolyte. So we have an anode, a cathode and an electrolyte, and in general the different types of fuel cells are described in accordance with the nature of the fuel used, for instance methanol or hydrogen, and also in accordance with the types of membrane and the types of the electrolyte. So we have a negative electrode in which the oxidations occur during discharging, acting as an anode, and the positive one, the cathode. In this case, basically, we have a flux of, for instance, let's make the picture more clear. We have a flux of the fuel. It could be, for instance, hydrogen. And here we have a gas diffusion electrode with diffusions of oxygen from atmosphere as oxidant. We have the fuel and we have the oxidant. So basically what is, and obviously here we have the electrolyte. There are different types of electrolyte, alkaline electrolyte, phosphoric acid and other types of electrolyte. Often we're even just using a proton exchange membrane maintained in a wet state, so obviously with an humidification due to the presence of water inside, but in general, basically the membrane is acting itself, if not dried, as an electrolyte. For instance, we are able to appreciate, and we will see in a moment, the use of proton exchange membrane. Proton exchange membrane, PEA, it stands for proton exchange membrane. These types of membrane composed of specific polymers, ionomers, that are basically polymers composed with a portion that is charged in order to, and a porous structure in order to ensure the mobility of cations, are basically able to allow the passage of cations without allowing the passage of electrons in order to avoid short circuit. We will see what it could be, for instance, the most important types of proton exchange membrane, the Nafion, speaking about the proton exchange membrane fuel cell in a moment. So basically we have this membrane, this polymeric solid electrolyte that is able to allow the passage of cations and avoiding the passage of electrons, and so avoiding the short circuit. So in order to understand what is actually the real working process of these types of fuel cell, we need to look at the discharging reaction. So we have in the negative pole the oxidations of the fuel. For instance, the release of 2H plus 2 electrons. What happens is that electrons are collected on the external circuit and are used in order to drive current. Whereas hydrogen is oxidized and we are generating the formations of H+. But this H+ can migrate inside the proton exchange membrane due to the conductive nature of this ionomer, Nafion, and can reach, for instance, the gas diffusion electrode when together with oxygen and the collected electrode can react in a reduction oxygen reaction. So the oxygen plus 2 times plus 2 electrons is give water. So basically we are creating the water from oxygen and the product of hydrogen oxidation. So we have here water that is acid. Obviously, this potential in standard condition is obviously equal to 0 volts, since this is the same reactions of hydrogen reduction, even if it is proceeding toward an oxidation, but is the same reaction, since we are involving the same redox couple. And also in this case, we have 1.23 in standard condition. So basically we can see how much the difference is literally equal with respect to the difference of the water line. And we can say in which way a fuel cell based on use of hydrogen as fuel, it represents a process that is something opposite with respect, for instance, the water electrolysis. And since we have basically the formations of water due to the interactions of these types of molecules, this is an exothermic reaction, since we are creating one molecule starting from more species, and so we have a little bit release of it. And it should be tuned and managed. So obviously on the anode we have this oxidation, but this oxidation is promoted with specific materials, and for this reason this electrode is composed of a porous electrode in which platinum particles are present, because the platinum is really able to catalyze really well the oxidations of hydrogen, whereas this is a classic GDE electrode that is composed of a gas diffusion layer. So basically we have carbon fiber in a carbon woven clothes, or maybe we can carbon fiber press it together in an amorphous way, and a sort of mat, not a real woven. We have obviously a microsporous structures of carbon particles with nanoparticles of platinum deposited over its surface in order to ensure both the conductivity due to the presence of a carbon structure and the catalytic effect due to the presence of platinum. So, and basically what is happening is that this is a conventional gas diffusion electrode. So we have a gas diffusion layer in order to ensure a good distributions of oxygen on the surface, in order to optimize the distributions of these species and avoidance problem connected to this homogeneity in the mass transport. And at the same time also this oxygen is able to enter within this electrode and reach the nanoparticles of platinum deposited on this carbon matter. And in this way basically the particles of platinum, they are acting as the catalytic side. So on the platinum basically these reactions is proceeding. But if this reaction is proceeding, we need to allow the passage of electrons on the particles of platinum, and this is due to the presence of carbon matter that can ensure a certain conductivity. We need to ensure the passage of oxygen, and this can be done just in accordance with the nature of the gas diffusion electrode, the porous morphology. But we need also to ensure the passage of H+, because we need to have all the reagent on the catalytic platinum side in order to have this reaction. And these types of H+ can be ensured, the passage of this H+ toward the catalyst can be ensured because even in the gas diffusion layer we can have a little amount of nathion, a little amount of ionomer, this conductive polymer that allow us to veiculate this H+ toward the catalytic side in which the reactions occur. So we can say that GDE in this case is composed with the gas diffusion layer composed of carbon fiber. We have a microsporous layer of carbon matter on which the catalyst, the platinum, is deposited over it. We have the nathion inside in order to allow the passage of H+, and we have even some traces of Teflon, polytetrafluoroethylene. Why? It's simple, because we need to improve the hydrophobicity. Why? Because we want to allow the spontaneous remotions of water when this is created as a product of the reaction, in order to avoid basically that the electrode is completely swelled from water. So we want to fill the electrode with water. The flowing of electrons should be avoided. And basically this is the reason for which it's so important to define all the components of the gas diffusion electrode. Here we have only a porous electrode containing platinum particles. Here we have a real gas diffusion electrode, because oxygen is taken from the outside, and so we have well-specific feature. We have a Teflon binder, we have a naphthalene in order to ensure the passage of these cations, we have carbon matter in order to ensure the conductivity, and we have just these amorphous, this porous structure that can promote the passage of oxygen. So this is extremely important. How extremely important is also the fact that in reality the platinum, even if is excellent for catalyze this reaction, is not so excellent for catalyze these reactions, and so we can have some electrical losses. And we are not able anyway to avoid this problem since there are no better catalysts. Obviously some studies are involving the use of cerium 4 oxide, but nowadays probably the most suitable choice is to remain platinum, even if we have some overtension connected with the use of this catalyst that is excellent in order to promote these reactions, but not so excellent in order to promote this reaction. So the use of platinum indicator is one other problem that should be solved. Obviously, together we have these types of problem, we have even another problem. We have, for instance, the fact that hydrogen that is filled inside as a fuel is often a product of some process and steam reforming, for instance. So when the methane is reacting with water, converted in hydrogen and carbon monoxide. Obviously we can have purification, and hydrogen is taken maybe from this process. But what is important to say is that since hydrogen is created together with carbon monoxide, some traces of carbon monoxide can be present inside this steam. And since this carbon monoxide can be present inside the steam, this is a really huge problem. This is a really huge problem because the platinum is extremely interactive with CO. So the carbon monoxide is absorbed a lot on platinum because the absorption energy of this species on platinum is higher with respect to this one. And so the platinum prefer to allow the absorptions of this with respect to this one. If we have, for instance, particles of platinum and we have particles of hydrogen here, so the red one represents hydrogen particles. Hydrogen molecules, the particles is the platinum particles, and the CO represent impurities of carbon monoxide molecules. The hydrogen prefer to absorb CO, and this is something really problematic because we are poisoning our catalyst and we are lose any activity and any possibility to generate H+ and ensure the proceedings of the reaction. And we can even regenerate the catalyst by rising up the temperature, because we need to say that when the temperature increases, basically the absorption energy of CO is decreased, and so we are promoting the remotion of this species, breaking down the force ensuring the absorption, and we can regenerate the catalyst just by rising up the temperature. And this is for what concerns the fact that we need to be aware on the use of fuel. They should be pure. Obviously, we can even use some traces of ruthenium in order to avoid this effect, but ruthenium is quite expensive, but is often used also in the gas diffusion electrode, ruthenium together with platinum, especially in all that types of fuel cell in which carbon dioxide is a product of the reaction. Why? Because even if not strongly as carbon monoxide, also carbon dioxide can cause the poisoning of the electrode. And since carbon dioxide is also taken from the atmosphere, sometimes it could be interesting to use ruthenium, but obviously the advantages are not so important if CO2 is taken from atmosphere in order to use these extremely expensive materials. But maybe we will see this aspect in direct methanol fuel cell when the carbon dioxide is directly the product of the reactions, and so is extremely close to the catalyst, when in that case use of ruthenium could be a solution in order to avoid the poisoning. So basically, another extremely important thing is to say is that this ionics membrane is working in a wet state. So it's working in a wet state since basically it should not be dried in order to ensure the passage of H+. And for the reason, proton exchange membrane fuel cell are basically working in a range of temperature. They should not be higher with respect 50 and 100 Celsius degree. So in general, we need to be lower, often 80 Celsius degree. Why? Because if you are increasing the temperature too much, we are promoting the drying of these types of membrane, and we are not able to promote anymore the passage of H+. And so it's important to say that in these types of fuel cell, the one based on a proton exchange membrane in a wetted state, we need to be aware on the temperature, the working condition, and we need to be aware on the management of water, inducing a quantity of binder Teflon really tuned inside the gas diffusion electrode, because in this way we need to have the right compromise between the right hydrophobicity in order to avoid the flowing, but we need also at the same time to ensure that the water presence inside the membrane is still remain present without undergo evaporations and drying. So basically this is just a matter of water management, that it should be completely tuned in the best way. Another aspect that is associated with the proton exchange membrane fuel cell based on these types of membrane is the fact that this membrane should not only able to avoid the passage of electrons and allowing the passage of H+, but should also be able to avoid the diffusions of gas. Because if the membrane is not built in the right way, we can have diffusions of hydrogen in this way, or maybe oxygen in this way, and we can basically have a lot of problems due to the interactions of these two types of matter inside the membrane. And so we need to avoid what a phenomenon known as gas crossover that should to be avoided. So now, after I've described basically all these aspects, it's important to look, but we will see this aspect in a dedicated lesson, which types of polymer is the solid electrolyte of the proton exchange membrane. And this polymer is the naphthion. It is a particular fluorinated polymer with a specific ionic structure that allows us these types of behavior. So in a dedicated lesson, in one of the next lessons, I want to focus my attentions mainly on the structure of the different types of polymer used in proton exchange membrane and even in alkaline anionics exchange membrane, because there are different types of fuel cell and even cells that are based on the use of an ionic exchange membrane. For instance, extremely interesting indirect methanol fuel cell in order to fight the gas crossover of methanol due to basically the opposites flowing of the anions with respect, for instance, a possible methanol crossover. But this is another aspect, and we will see this concept in one of the next lessons. So what is important to say now is what are the general features of each single fuel cell, and in this case today we have discussed about the structure of the proton exchange membrane, the gas diffusion electrode, and in general the proton exchange membrane fuel cell based on the use of hydrogen as fuel.